New Orleans is a very special place, culturally, and a big city, but built in the wrong place really. So it's low-lying, it's at risk of hurricanes striking it, and that's why it's protected by a system of levees. Hurricane Katrina happened in August 2005, and the combination of the severity of the storm and the path that it happened to take led to a storm surge of about 9 meters. So the water level was 9 meters higher than normal. There was not just water coming over it, but it also caused breaches, collapse of the defenses in about 50 places. The consequences were dramatic, $125 billion of economic damages, and something like 1,500 people died. It was a national scale disaster obviously, so the United States Congress gave the United States Army Corps of Engineers the job to redesign and restore the flood defense system. As originally a Dutch company, I have a really strong track record in designing and helping operate big flood defenses. The Netherlands are a very low-lying country, a bit like New Orleans, but very well protected. And so that experience we were able to use. For the project as a whole, there was the really big question of a city that had emptied after the storm, and the project had to essentially create confidence that this was still a place worth living in. So that was at a big scale, that was the challenge here. Do we still want to have New Orleans there, where it is? And so the quick turnaround of being seen to be improving the defenses and creating that confidence was very important. So this idea of resiliency, people knew that people had died because of the collapse of the defenses. What are you going to do about that? And just a single line, they have to be resilient, is just a single line, but how to translate that to something real that is meaningful and still cost effective, because the budget was also limited. So how do you do that? How do you design a flood defense, a levee system that can withstand that 1% storm, but also doesn't collapse in an even more extreme storm? So I would say the timing, programming, and that special resilience element, they were the key challenges. An important part was walls like this. So historically they used like concrete eye-shaped walls. One of the main reasons why the defenses collapsed during the storm was that there was water overtopping, scouring out the ground, and then those eye walls fell over. And so a big part of the different approach was to construct T-walls instead of I-walls. So that's an inverse T, so the wall sticks up, and then there's a flat bit on the ground to stop it from collapsing and from the ground washing away. A key element that we did was the modeling and data analysis to determine how high the flood defenses had to be. So that's a big, important part. And we also played a big role in the resiliency. So that resiliency element of the remit that the engineers got is not so straightforward, because that's not normally the remit that you get from a client. Normally your remit is design this to withstand the storm. So this was a special case, and so we helped the clients to get their head around that. So what does that mean? How do you translate that concept to practical design rules to design and build your defense? And we also wrote the armoring manual that they developed. So how do you design a rock revetment and armoring to protect that landward slope? Now we had to translate originally Dutch design rules into the American context, and the big difference there was tropical grass. So grass in tropical areas like New Orleans is much stronger, so we had to use laboratory tests in a big full-scale laboratory in Colorado and translate that to, so what sort of overtopping can a good New Orleans grass cover withstand? And that then fed into the decisions of, so where is the grass good enough? Where do we need geotextile mats, or where do we need rock to protect that slope? Another thing that we did in the project was we developed a number of smart tools, smart digital tools to help the local flood defense managers manage flood risk. So one of them was a hurricane storm atlas, essentially combining information from a lot of historic hurricanes. How strong are they? Where do they come to land? And to help people predict how high the water levels and then the waves would be, so that they could prepare and start evacuations when there was a big storm brewing out in the Gulf of Mexico. And the other thing was a levee information management system, essentially a dashboard for the flood defense managers to see if the water level is here, then I need to close this and this gate, and I need to start now because then I'm ready in time to close the gate before the water comes. The first step in 2006 was ready on time, and by the time it was 2012, well, as planned, the system had been rebuilt to that 1% standard, so at least that was there. And they then took a bit more time to also to install those revetments and those geotextile mats to create that resiliency. But that's now in place. When you look at how the city has developed and has sort of re-emerged after 2005, well, you can see that it has created the confidence that that was needed. The flood defense reconstruction after Katrina in New Orleans shows the value of civil engineering to society. If the civil engineers here hadn't been able to instill that confidence by doing a good job and thinking of what actually went wrong, responding to those concerns that people have, well, the community wouldn't have had the confidence to go back. The New Orleans project for me is a great example of going to a totally different place that you've not been before, a really exciting place. Get your head around the challenges locally. In this case, for example, well, different types of grass. How do I translate my knowledge of existing design rules to this different context, and then do something that really helps to recreate a city as magical as New Orleans.